Okay, so for chapter 4, this is going to be the beginning of our stoichiometry. Stoichiometry is when we can look at a chemical reaction and answer questions like how much of this product should I get from using this much reactant, or how much reactant do I need to produce this much product? So those are the kinds of questions that we're going to be looking at. And so the first thing here is just balancing some very generic chemical equations. We're not looking at specific types just yet. So this is just getting used to the law of conservation of mass. I kind of think of the arrow as an equal sign where I'm trying to make both sides equal. So there's a few, I wish I could say there's always a right way to do balancing equations, and there really isn't. It depends on the reaction type. So as we go through the next chapter and the one after, we'll start looking at specific types of reactions like double displacement or single displacement or combustion. And then we'll have ways of predicting those products because we'll recognize what type of reaction it is and balancing them out in a more easy way. But in this case, we're just kind of starting generically. We're given both the reactants and the products. All we're trying to do at this point, see, there goes my video. All we're doing at this point is making sure that we follow the law of conservation of mass. And so what we mean by that is, if I look at this first equation, I want to have the same number of silicons on both sides, the same number of chlorines on both sides. So the big thing here to capture is the difference between the subscript and the coefficient. So chapter 2 was all about the subscript when we were doing nomenclature. So SiCl4, metalloid silicon, often that takes the naming system of a covalent compound. So silicon tetrachloride reacting with water to make silicon dioxide. And then HCl is actually a funny one. If it's in solution, it would be hydrochloric acid, which is the binary acid system we learned in chapter 2. Technically, if it's in its gas state, then we call it hydrogen chloride. But I always name these assuming the acid form because typically they're mixed with water. But at least in my use of it, that's my day to day. Anyway, so we got SiCl4, H2O. Those are the reactants. They're producing SiO2 and HCl. Those are the products. And when I go to balance this, there's not really a perfect way to start. What I always try to look for first, though, is if there's an element that starts out in one place on the reactant side, but then goes to two places on the product side. So it splits apart and goes to two different products. I always do that one at the very end. I get everything else done and then I do that one last. This one doesn't have that. All the silicon goes from one place to the other, right? So one place on the reactant side, one place on the product side. So silicon at this point looks balanced. If I go to the chlorine next, just sort of going in order, there's 4 chlorines obviously on the reactant side, but I've only got 1 here on the product side. So I need to multiply the HCl by 4. Now that 4 gives me the 4 chlorines, but it also gives me the 4 hydrogens. So the big thing here is understanding the difference, the purpose of the subscript versus the coefficient. The subscript obviously is to get the correct compound formula, right? We know water is H2O. We looked at that with the law of constant composition. Water is always H2O, right? We don't change those subscripts because then we don't have water anymore. The coefficient in front is what we're looking at here just to balance both sides of the equation. So since we've got 4 chlorines on the reactant side, we need 4 chlorines on the product side. We've only got 1, so we multiply by 4. Now that 4 in front applies to the chlorine and the hydrogen. So I'm just going to check hydrogen next. I've got now 4 hydrogens on the product side. When I look on the reactant side, I only have 2. So I need to multiply water by the multiple of 2 that will get me to 4. So 2 times 2, so 2 in front of water. That gives me my 4 hydrogens. That matches my 4 hydrogens on the product side. And that 2 in front also obviously applies to oxygen. 2 oxygens matches the 2 oxygens and the silicon dioxide on the product side. So that is a balanced chemical equation. Then for the next one, I've got PCl5, another covalent compound. So we would name that as phosphorus pentachloride. Water again, second reactant. The H3PO4, assuming it's in solution, right, because there is water present, that would be phosphoric acid. That's the phosphate polyatomic ion, phosphoric acid. And then again, the hydrochloric acid, binary acid, remember, always gets the hydro in front. So that's a little kind of review of chapter 2 material, nomenclature. All right, so what I had mentioned was if you have an element like hydrogen in this example that starts out in one place on the reactant side and goes to 2 different places on the product side, right? It splits apart and goes to two different products. Always do that one last. Everything else, try to get in all in place. There's one phosphorus on the reactant side, one on the product side. Phosphorus looks good. Then I go for 5 chlorines and the pentachloride. I check my chlorine on the product side. I've only got one in the HCl. So I'm going to multiply HCl by 5. So that fixes 5 chlorines on both sides. I'm not going to look at the hydrogen, right? Because again, there's hydrogen in 2 places here. So there's one more element to do next. That's the oxygen. When I look at that PO4, the phosphate, there are 4 oxygens there. In the water, there's only 1. So I need to multiply the water by 4, right? So now I've got my 4 oxygens. Yeah, this is the chapter 4 notes. This is the 4 oxygens to balance the 4 oxygens on the product side. And now the last thing I'm going to look at is the hydrogen. Because every other element is balanced, I'm really hopeful that hydrogen is also balanced, right? So the 4 in front of water, H2O, means I've got a total of 8 hydrogens there, 4 times 2. So I need 8 hydrogens on the product side. I've got 3 in the H3PO4 and another 5 with the 5 HCls. So 5 hydrogens plus 3 is a total of 8, and that matches the 8 that I have on the reactant side. So that is another balanced equation. All right, there goes my video. For the third equation, now we have an ionic compound. So this is calcium oxide. Binary compounds always end in IDE. Covalent compounds, so tetra, phosphorus, deca, oxide. And on the product side, this is calcium phosphate, Ca3PO42. All right, so in this one, if I start with the calcium, right, it looks like 3 calciums on the product side. On the reactant side, there's only 1. So I'm going to multiply the calcium oxide by 3. That fixes the calcium. I'm going to do oxygen last because it's in 2 places on the reactant side and only 1 on the product side. So I'm going to do oxygen at the end. Let me check phosphorus next. I've got P4O10. So I've got 4 phosphorus there on the reactant side. On the product side, distributing that 2 in the parentheses, there are 2 phosphorus. So I've got 2 phosphorus on the product side, but 4 on the reactant side. So the calcium phosphate on the product side, I'm going to have to multiply that by 2. So I had 2 phosphorus and then I multiply that by 2. So now I have a total of 4, and that matches the 4 that I have on the reactant side. Now, what I have to think about though is I thought calcium was balanced, and now putting that 2 in front of calcium phosphate means I got to go back and check that. Because that 2 obviously applies to calcium as well. So 3 subscript times coefficient 2, I've got a total of 6 calciums. So back in front of the CaO on the reactant side, I'm going to change that 3 to a 6. And so sometimes that just happens. There's no way to really work around that. Now the oxygen, what I look at here is the 6 in front of CaO, that gives me 6 oxygens, plus the 10 that's in the tetraphosphorus deca oxide. So 6 plus 10 means I have a total of 16 oxygens on the reactant side. Now on the product side, a lot of little numbers to think about here. The phosphate group is times 2. So the O4 times 2 means there's 8 total oxygens here times a 2 coefficient. So 4 times 2 is 8, times 2 is 16. So I have a total of 16 oxygens as well. And I don't know why I put a Z, oxygens as well on the product side. So that is now balanced. So sometimes when you're balancing the equation, you can't avoid having to kind of go back and retrace your steps because you think something is balanced and then you have to change the coefficient. And then of course that changes, it's a domino effect, right? So that's okay. Now, one of the things I had mentioned in the introduction for this section is when you go to balance, if you have a polyatomic ion that stays as the polyatomic ion on both sides, it's easier to just balance it as a unit. In this example that we just looked at, the phosphate doesn't stay phosphate on both sides. So we had to break it apart and look at phosphorus and oxygen separately. But in D, example D, we've got hydroxide, which is OH. And that stays hydroxide on the product side. So we can balance that as a unit. It's going to make it a little bit easier, especially when we get to E, where you see oxygen in every single reactant and product. That can be tricky unless you keep the polyatomic ion and balance it that way. It'll be easier. But we'll get to E next. So when I look at D, I've got FeCl3, iron type 2 metal, so iron 3 chloride, reacting with sodium hydroxide to make iron 3 hydroxide and sodium chloride. All right, so when I first look at this, the metals actually look balanced. 1 iron on both sides, 1 sodium on both sides. So now if I look at the chloride, FeCl3, I've got 3 chlorines on the reactant side. On the product side, only 1 in the NaCl, so I got to multiply NaCl by 3. All right, and that obviously changes my sodium, right? My sodium is no longer in balance. So now 3 sodiums on the product side. Now on the reactant side, I need to put a 3 in front of NaOH. That'll balance now 3 sodiums. That gives me 3 hydroxide groups, and that matches the 3 hydroxide groups on the product side. So now I've got a balanced equation. 1 iron, that didn't change. 3 chlorines, right? And then I've got 3 hydroxides and 3 sodiums. So that equation is now balanced. Now the last one here is where balancing the polyatomic ion as a unit is going to be extremely helpful because, right, oxygen is everywhere. So if you looked at oxygen individually, it would be really, I think, challenging to say, where am I going to put the coefficient to make sure everything's working? So what I look at here first, there's 1 barium on both sides. So barium appears to be good. When I look at aluminum, aluminum is not in balance. I've got 2 on the reactant side, but only 1 on the product side. So in front of that aluminum nitrate on the product side, I'm going to multiply by 2. Come on, video. There we go. All right. So 1 times 2. So there's my 2 aluminums. All right. So now I've got 2 aluminums on both sides. Barium, we're still thinking is balanced at 1, but we'll see what happens. All right. So now when I look at polyatomic ion, it's up to you where you want to start with. If I start with nitrate NO3, I've got 2 of those groups on the reactant side, subscript of 2, so 2 nitrate groups. On the product side, I've got 3 groups in the aluminum nitrate times 2. So 3 times 2, I actually have a total of 6 nitrate groups on the product side. And on the reactant side, I only had 2 nitrate groups. All right, so this is where knowing your polyatomic ions is really helpful because you recognize that nitrate is a unit and you don't break it up. It stays easy to balance that way. Now, obviously 2 and 6 not balanced, right? So I'm going to have to multiply that barium nitrate on the reactant side by 3 because now, 3 times 2, now I have a total of 6, right? 6 total nitrates to balance my 6 total nitrates here. Now, when I did that, that obviously changes the barium as well. So 3 bariums on the product side, there's only 1. So multiplying barium sulfate by 3. Now I've got 3 bariums, 3 bariums. And now we can check sulfate. I've got the 3 in front of barium sulfate meant 3 sulfate groups. And on the reactant side, I've got 3 sulfate groups. So now at this point, everything appears to be balanced. Now, when you balance your chemical equations like this, students always ask, do I have to put a 1 in front? That's up to you. If there's no number in front, it's an implied 1. So if you feel better writing in the 1, then write it in. If you don't want to write it in, you don't have to. It's just when you need more than 1, obviously, that you have to have the number. So what this tells us and what we're going to now segue into is the stoichiometry part of this. And what we want to recognize in, if we go back to what we talked about last week, sorry, not last week, Tuesday, 2 days ago, is that we use the mole in chemistry to substitute 6.022 times 10 to the 23rd particles. So again, rather than thinking of this reaction that we just looked at as 3 molecules of barium nitrate, technically formula units because it's an ionic compound, but that's again splitting hairs, reacting with 1 molecule of aluminum sulfate to make 3 molecules of barium sulfate and 2 molecules of aluminum nitrate. What's easier is the substitution of a mole. So this tells me that 3 moles of barium nitrate react with 1 mole of aluminum sulfate to make 3 moles of barium sulfate and 2 moles of aluminum nitrate. And that's what I have for you written right underneath that. So what those coefficients in front give us are what's called the molar coefficients, right? The coefficients in front, and they are telling us how many moles, right? So these are the molar coefficients. Let me grab my highlighter really quick. And we're going to use these in the step for stoichiometry, which is the mole ratio step. And in all of your stoichiometric calculations, period, right? Exclamation point in all of them, the mole ratio is the center step. Because if we're trying to compare 2 different substances in a chemical reaction, The only way to do that is through what I think of as the recipe, right? If I want to know how much aluminum nitrate I'm going to make in this barium nitrate plus aluminum sulfate reaction, I have to know what is the relationship of the aluminum nitrate to the reactants, right? So if I start with this much reactant, how much product am I going to make? The only way I can compare those is through the balanced equation. So those mole coefficients, those numbers in front, tell us that relationship. And so anytime we compare two different substances in a chemical reaction, we have to pass through that recipe, right? That the mole ratio. So here's our first example. We've got a combustion reaction of propane, which is propane is C3H8, PROP means 3 carbons. And we're reacting it with 5 oxygens. It makes 3 carbon dioxides and 4 H2Os. And this question is asking how many moles of carbon dioxide are formed when 0.529 moles of propane are burned. So when I was a student, what I always did is I used my equation as my organizing tool. That was just me. So I kind of looked at it and said, okay, I'm going to use my equation. I'm going to write down what I know, what was given to me in the question. And that is that I have 0.529 moles of propane. And then I always write down what I'm looking for. So I wanted to know how many moles of CO2. So the way I always kind of think about this is your starting point is always your A, your question mark is always your B. It's always where you're headed. So this calculation here is not, it's not a very common one that you're going to do in chemistry, right? Imagine if you go into lab or you go out to your gas grill and you're burning your propane, right, in your tank. The question's probably going to be more like, okay, I've got, I don't know, 5 liters of propane in my tank, whatever you can substitute, whatever you want there. And I want to know then what volume of CO2 would I make from this combustion reaction, right? So I'm going to use this much propane. Maybe you know how many grams you have. Maybe it's 150 grams. What volume of CO2 will you make? That calculation is much more characteristic. Where we start though in stoichiometry is going through what I just referenced is always that center step, which is relating the two substances together, which can only be done through the chemical equation. So what I mean by that is like, if you go in the lab, we don't have scales that tell us how many moles we have. If I took my sample of propane and put it on a scale, it's not going to tell me how many moles. It'll tell me grams. Maybe it's a volume that I'm measuring, right? We don't have moles, right? But this is the center step. So we always start here in stoichiometry and then we build. So whenever you're relating two substances in a chemical equation, you can only do that through the mole ratio. And from our balanced equation, what we know is that for every 1 mole of propane, right, no number in front, so it's a coefficient of 1. So for every 1 mole of propane, we make 3 moles of CO2. All right, and MOL or MOLE, depending on how you want to write it, either way is fine. So there's my conversion factor, right? So when we started chapter 1, we looked at 1 kilogram as 1,000 grams, right? So it's the same idea. It's just this is our conversion step when we do chemistry. When we look at two substances, we have to look at the balanced equation to get that relationship. So we always start with what we're given. Question told us we had 0.529 moles of C3H8. All right, now when I set up my conversion step, I want to get rid of moles of C3H8 on the bottom, and I'm going to go to moles of CO2 on top. All right, so as we get more and more into stoichiometry, what I always want to tell you is when you have your units, technically there's 2 things you're writing down. You're writing down the unit and the substance. And in each conversion factor, only one thing can change at a time. So in this case, the substance is changing, but the unit stays the same. And the only way the substance can change is if the unit is mole and mole, right? That is what this balanced equation tells us. But for every 1 mole of propane that I react, I produce 3 moles of CO2. So basically we're setting up a ratio, right? If I know that 1 mole of propane makes 3 moles of CO2, well, I only have 0.529 moles of propane. And so that means I would only make 1.59 moles of CO2. So I'm just taking that 0.529 and multiplying it by 3. And then as we always do with our calculations, we check our significant figures. The mole ratios, those are perfect numbers. The 1 and the 3 don't limit the sig figs. We go with that starting measurement, which had 3 sig figs. So our answer here will also have 3 sig figs. All right, so that is the center point of every, and I do mean every chemistry calculation that you do when you're comparing two substances. You have to go through that mole ratio. All
Excuse
right.
me.
Yeah, go ahead.
On the test, if will it be worded like 0.529 moles of propane? Because what if we don't know the chemical formula for propane?
Yeah, no, propane, like you could probably look at the equation here and figure out that that would be propane because it's not carbon dioxide and not water, but no, that it'll be given to you as C3H8.
Okay, thank you.
Yep, you're welcome. All right, so the mole ratio, always the center step. So let's try another one. Now what we're going to do is, like I mentioned, we'll add to it, right? Because if we, that's not like a very common calculation we're going to do. We're not going to walk into lab and measure how many moles we have, but we might measure the mass that we have or the volume, right? So this question, we've got titanium 4 chloride, TiCl4, reacting with elemental magnesium, which makes titanium and 2 moles of magnesium chloride. Question says, how many grams of magnesium? So underneath magnesium, I just put question mark grams and I labeled that that's my B, are going to be required to convert 83.6 grams of titanium 4 chloride to titanium metal. All right, so we're starting with the titanium 4 chloride. I'll mark that as my A. And we want to know the mass of magnesium we need to do that reaction. All right, so we're putting those two things together. What mass of magnesium are we going to need for that reaction? Oh, come on, video. Okay. All right. So this one's different. We had moles in the last example. This one's got grams, right? And again, that's going to be, that's a better example of what we would do if we walked into lab, right? Now, what I want you to recognize is anytime that you are asked for grams or you're given grams, you still always have to go through that mole ratio center step, always, right? So if you think about this, we've got the mass of the titanium 4 chloride, so that's our A. You have to first go to moles. So I always say that if in doubt in chemistry, always go to moles. It is the center point. Because once I get to moles, I'll be able to switch my substances and go from A to B. And then from there, I can take moles to mass using a conversion factor that we learned in the last chapter. All right, so building onto this, this is sort of the stoichiometry part, mass of A to moles of A to moles of B to mass of B. The mole ratio is what we're learning in this chapter. That's the center point, right? From the balanced equation, what ties those two substances together. And what we want to remember from the last chapter is if we're relating mass and moles, we use the molar mass from the periodic table or molecular weight or whatever you want to call it. I like molar mass. And that's what we talked about on Tuesday. So before I can really do anything here, I'm going to have to go get my conversion factors, right? I can't, they're not something I memorize. They just, I have to get them from the periodic table. So when you read a question, if the question is asking you for grams, I want you to think automatically periodic table. So I need magnesium, the molar mass from the periodic table. Remember, go 2 decimal places, so 24.31. And then I'm going to need also the molar mass of the titanium 4 chloride. So TiCl4, when I go to my periodic table, the titanium is 47.87. All right, and then I also need to find the chlorine, which is 35.45. But because of that subscript of 4, I need to take that 4 times. So the 35.45 times 4 is 141.80. And then I'll add that to the 47.87. And I get here 189.67 grams per mole. All right, so those are the conversion steps I need to do this problem. So if you have grams, you know, okay, periodic table. Magnesium, 24.31. Again, that's the mass number that we looked at on Tuesday. And then the titanium 4 chloride, I've got mass, so I know I need molar mass. So I went and got my titanium, my chlorine, because there's 4 chlorines here. I multiplied the chlorine by 4. All of that together was 189.67. Okay, so now we're ready to get started. Now, molar masses, right? What we just found on the periodic table, those are constants. You never start with constants. Constants are the conversion factors. They go in the parentheses. You always start with what you're given, right? So we have 83 0.6 grams of the TiCl4. All right, then when I set up my first conversion step, I know I need to get rid of grams of TiCl4. If in doubt, always go to moles of TiCl4. All right, now grams per mole, that's our periodic table. So 189.67 grams on the bottom. And that molar mass is always based on having 1 mole. That's from our periodic table. So we put 1 with the mole on top. Now in the next conversion step, we're going to put mole of TiCl4 on the bottom. And as I mentioned, right, only one thing can change at a time. So in this first conversion step, the substance stays the same, but the unit changes. Now in this one, we're going to change substances. We're going to go to magnesium, but only if the unit stays the same. So mole and mole. This is where we go up to our balanced equation. And the balanced equation tells us for every 1 mole of titanium 4 chloride, we make 2 moles of magnesium. All right, so that center step right there, that mole ratio step, that is always going to be how we tie 2 things together from our balanced equation from the recipe, right? And that mole ratio has to go in the middle of all your stoichiometric calculations. You cannot skip that step. Now, one more step to go here, because we obviously want grams of magnesium, because that's what the question was looking for, but we need to get rid of moles of magnesium on the bottom. Now, here's where sometimes I'll see students take a detour. They go up and they look at the equation and they say, okay, well, there's 2 moles of magnesium here, so I should put 2 moles again on the bottom. But your molar mass value from the periodic table is always based on 1 mole. So when I put the 24.31 grams on top, it's per 1 mole of Mg. And that factor of 2 from the balanced equation, the coefficient, we already factored that in. So we don't need to do it twice. We already did it, right? So this first conversion step tells us how many moles of titanium chloride or titanium 4 chloride we have. The second step tells us how many moles of Mg we need. And then the third step tells us what mass that would be. So following the units, getting rid of grams of TiCl4, next getting rid of moles of TiCl4, and then last getting rid of moles of Mg. And this will tell us what mass of Mg that we need. So I'm going to take the 83.6, divide it by 189.67. That was the molar mass from the periodic table. Multiply by 2, and then multiply by 24.31, again, the molar mass from the periodic table. And then always at the end, right, sig figs. So my starting measurement has 3 sig figs. So my answer here is going to be also 3 sig figs. And I get 21.43, but it just is going to round to 21.4 grams of magnesium. All right, so that would be the mass of Mg I would need to react with that mass of TiCl4. So stoichiometry, right? We're pulling in what we learned in chapter 3, molar mass with mole ratio, right? So just kind of bridging everything together. We're going to try another one of these. All right, and again, this next example, probably not as common of a calculation because we're trying to see how many molecules of carbon dioxide we would need. All right, sorry, my video keeps doing that. To be or would be produced, sorry, from the combustion of the 225 grams of octane, octa, right, 8, so 8 carbons, so C8H18. All right, so this one, again, not as characteristic because we typically don't measure or calculate molecules because again, that's why we use the mole anyway, is that we don't have to do that. We can just look at kind of more relevant quantities like grams, right? Rather than counting molecules. But I want everybody to sort of remember what the mole is representing, right? So that's why we're going to look at this calculation. So if I think about my flow chart here, I'm starting with a mass of the octane. That's going to be my A. So just like we did in the previous example, we always go to moles first, right? That will never change. So we are going to first take mass of A to moles of A, and that's where we're going to need the molar mass from the periodic table. So again, when you see grams, you think periodic table, right? Then mole of A, we're going to switch and go to moles of B. That's always your center step, right? Going from the octane to the CO2. And then here, the last step is a lot of times students, like especially in the homework problems, we do a lot of mass calculations and they think kind of automatic, okay, I'm going to go get molar mass from the periodic table. But if we're looking for molecules, we don't need molar mass. Instead, we're going to need Avogadro's number. So we're going to take moles to molecules and we're going to use Avogadro's number for that, the 6.022 times 10 to the 23rd. All right, so before I can get started here, I need my molar mass of the octane. All right, so let me get that. So molar mass of C8H18, 8 carbons at 12.01 apiece, and then 18 hydrogens at 1.01 apiece. So 8 times 12.01 plus 18.18, I get 114.26. All right, so 114.26 grams per mole. All right, so now I'm ready to start. I've got my conversion factors, I've got my flow chart. I'm going to start with what I was given. I have, oh boy, I have 225 grams of C8H18. On the bottom, I need to get rid of grams of C8H18. So that's where that molar mass is going to come in. So from the periodic table, when I added that up, that was 114.26 grams. Oh boy. Okay. And then on top, that's always per 1 mole. Remember, molar mass is always based on 1 mole. So don't look up here and see that 2 and think, oh, I need a 2. Nope, that's the next step. So molar mass is always just based on having 1 mole. In the next step, we're going to go and we're going to take our moles of C8H18 and switch it to moles of CO2. And that's this step right here. When we change the substances through the mole to mole ratio is when we go and grab those coefficients. So on the bottom with the octane, we're going to have that coefficient of 2. And then on the top with the CO2, we'll have that coefficient of 16. All right, so for every 2 moles of octane, we make 16 moles of CO2. And then the last one here, for each mole of CO2 that we make, we have 6.022 times 10 to the 23rd molecules, right? And again, just sort of remembering why we use a mole in the first place, right? So instead of counting every single particle, right? We don't want to do that. We have this representation. So yes, mass is probably more likely something that we would calculate like we did in the last example, but I just want everyone to remember why we're using this mole in the first place. So 225 divided by 114.26 times 16 divided by 2, and then multiply that by 6.022 EE23, and we'll keep our 3 significant figures. So I get 9.49 times 10 to the 24 molecules of CO2. All right, so that would be using Avogadro's to calculate particles. All right, so in both of those questions, we were starting with the mass of A, whatever that substance was. And molar mass is what takes you to moles. So the periodic table gives you that conversion factor. Center step, once you have moles of A, you go to moles of B. That you have to do that. That's from the balanced chemical equation. That's our mole ratio. And then where do you want to go? If we want mass, molar mass again is what we're going to use. If we want particles, then we're going to use Avogadro's number. All right, so in both of those examples, we only had one reactant and we were going from one thing to one thing. Sorry, so if I say that, what I mean by that is we had 1A, we went to 1B, right? We knew where we were starting, we knew where we were going, we just had one calculation to take care of. The next thing we have to talk about though is we could have a limiting reactant problem. So like in the last example, when we were looking at the octane producing CO2, the oxygen wasn't mentioned. So we just assumed that it must be present in excess, right? That we would have enough of it to make as much CO2 as we needed based on that amount of octane. But what if that's not the case? Like, what if I started over with this question and I said, okay, we've got 225 grams of octane, but I only have 100 grams of oxygen, right? So now the question is, how much CO2 will I make based on those 2 reactants? And that becomes a limiting reactant problem. And what that means is one of those reactants will run out first and thus limit how far the reaction can go. And a lot of times, unfortunately, it's not like you can just look at the numbers and guess which one is limiting. So what you have to do here is if you have a limiting reactant problem, what you're going to recognize is that you're given two quantities of reactants. That's what's different. Instead of just having one reactant, you're going to have two quantities of reactants. And that'll be your signal to say, oh, okay, I get to do two calculations instead of one. Lucky me, right? And you're always going to be looking for a product. You know, limiting reactant problems are always written that way. You've got this much reactant A, this much of the other reactant. How much product can you get? And so what you want to always do with these, at least this is the way I always do them. There are teachers do them differently. This is the way I think is the most direct. This is what I thought felt to me like the most efficient way to do it. Is I have reactant A1 and reactant A2, right? I've got two reactants this time. I'm going to take my first reactant and figure out how much product I can make. Then I'm going to start over and take the second reactant and figure out how much product I could make with that one. And then what I'll figure out is based on those two answers that I get, whichever one produces the smaller amount of product obviously limits how far the reaction can go. So what you want to keep in mind is that when we do these calculations, these stoichiometry calculations, when we get our answer at the end, it is telling us, yes, we've made this much product, but all of that reactant that we started with is gone. It's all been converted to that much product. So when we go through these calculations, we'll figure out how much product the first reactant could make. Then we start over and we figure out how much product the second reactant could make. Whichever one produces the smaller amount is the limiting reactant, and that is the most amount that you can make. So the smaller number is your max yield. And I know that seems counterintuitive, but it's just because the smaller number is what's produced by the limiting reactant. When I mix two things together, like if I go back up here with the octane and the oxygen, at some point, one of those is going to run out. And when that happens, the reaction comes to a stop. All right. So when we do these calculations, one of their terminology before we turn the page, when we do these calculations and we get our answer, these are called theoretical yields. In theory, if everything's perfect, this is what we should get. If we go into lab and we do the experiment, we're probably going to get actually something different. And we'll look at a percent yield coming up. But when we do these stoichiometric calculations, the answer we get here is always theoretical, right? In theory, that's what we should get. All right, and that's what's listed down here at the very bottom. The actual yield comes from actually doing the experiment, right? And so those are the types of things we can get when we're in lab, for example. But in this class, it would have to be given because we're not actually doing the experiment, all right? So we're also going to look at calculating a percent yield, and percent yield is defined as the actual yield over the theoretical yield times 100. All right, and we'll look at calculations for that coming up. All right, before we get there, I've got a stoichiometry calculation here for us to do. I've got iron 2 sulfide reacting with 2 moles of hydrochloric acid to make iron 2 chloride and well, this one, yeah, I'll just say hydrosulfuric acid, but since it's a gas, technically it's dihydrogen sulfide. But we've got 10.2 grams of HCl, and we are adding it to the 13.2 grams of FES. And the question is saying, how many grams of the hydrosulfuric acid could we make? All right, so you see how this one's different? We've got our first reactant, we have a second reactant, and we're looking for how much product we could make. All right, so instead of getting to do just one calculation, we get to do 2 calculations. So we're going to have 2 different answers, but we have to figure out of those 2, which is the correct one. So again, this is my format that I always like to do is I take my A1, go all the way to B, start over, take your A2, go all the way to B, and then at the end, we circle the smaller. All right, now what types of things am I going to need here? Both of these are taking mass to mass, right? So we know, like we looked at with the titanium 4 chloride and the magnesium, we're going to have molar masses from the periodic table. So I'm going to use this space up here to get my molar mass values. I think I'll have enough room. Actually, I'll have enough room here, so I'll just do it here. All right, so the FES, all right, if I go to my periodic table, iron is 55.85, sulfur 32.07. Don't feel that you have to write that down. I'm just trying to show you where the numbers are coming from. So FeS molar mass 87.92. The HCl, the hydrogen is 1.01, the chlorine is 35.45. So this one is 36.46 grams per mole. And then the last one, the dihydrogen sulfide or hydrosulfuric acid, the two hydrogens 1.01 apiece, and the sulfur 32.07. And the answer I get there is 34.09. All right, so I got all my molar masses that I need to do all my calculations, so that's good. So now that I've got my conversions, I'm going to start by taking A1 going to B. All right, so for my A1, I had 13.2 grams of FeS. First conversion, right? Always go to moles first. So molar mass is going to help us get from mass to moles. The iron 2 sulfide, 87.92. Oh. And that is the mass of FeS per mole. All right, then our mole ratio from the balanced equation for each 1 mole of FeS. All right, make sure you always go to your product. We're going to go to the H2S, which also has a coefficient of 1. So 1 mole H2S. All right, so I'm going to pause here for just a second. A lot of times this is another place where I'll see students go sideways, because when you go back up to the question, you see the FeS and you see the HCl. So a lot of times I'll have students take FeS to HCl and then HCl to FeS. And to me, when I think about that, like my brain says, well, you're just going in a circle. You know what I mean? Like I'm going here to here and here to here. I always want to go forward. So make sure you're always going to the product, to the question mark, right? So we know that we're going to the H2S for this, the product side. All right, so starting with mass, went to moles using molar mass, then we switch our substances through the mole ratio, and then to get to grams, we need the molar mass. So for the H2S, that is 34.09 grams. Whoops, I don't know why I made that S so big, sorry. I think I was thinking parentheses. Okay, so 13.2 divided by 87.92, and then times 34.09. And to 3 significant figures, I get 5.12 grams of H2S. All right, now keep in mind, if this were a multiple choice question, that answer would be a possibility, but we don't know yet if that's the right answer. All right, because that calculation, when we do it, right, the sulfur is coming from the FeS, but the hydrogen's coming from the HCl. And when I did this calculation, I'm just looking at the sulfur, really. Like, did I have enough sulfur from FeS to get here, right? But I now have to go back and figure out, okay, well, the HCl, that supplies the hydrogen. So this first calculation I did assumes that I have excess HCl, and I don't. I have only 10.2 grams of it. So that's why you always have to do 2 calculations when it's limiting reactant. So now the A2 to B. I've got my 10.2 grams of HCl. Oh, this is going to drive me crazy. Okay, 1 mole of HCl is 36.46 grams of HCl. Mole ratio in this case is 2 moles of HCl for 1 mole of H2S. All right, and again, I'm pulling those numbers right from the balanced equation. It's a 2-to-1 ratio. And then 34.09 grams H2S is 1 mole of H2S. All right, so on my calculator, 10.2 divide by 36.46, divide by 2, and then times 34.09. And here I get 4.77 grams of H2S. All right, so I know it's always tempting to look at the starting quantities and assume you know which one's going to be limiting. And it kind of looked like it worked out for this one, but that's not always the case. Because remember, the masses are different, but the molar masses are very different. The mole ratios are different. So you can't look at the initial numbers and just assume you know which one's going to be limiting. You got to go through the calculations. So basically what our calculations told us is we had enough FeS to get to 5.12 grams of H2S. But with the HCl, I only had enough to get to 4.77 grams. So that 4.77 grams, that is our max theoretical yield, right? It's a little counterintuitive that the smaller number is your max yield. But what this tells me right here is that the HCl is going to run out first. So this is my limiting reactant, LR. It also tells me that the FES, I'm going to have some of that present in excess, right? There's going to be some of it left over at the end. And that smaller number, 4.77, is my max theoretical yield, TY, right? So remember, in theory, if everything's perfect, this is what we should get, the 4.77 grams. But if we went into lab and actually did it, we probably wouldn't get that, right? Because, you know, that's just how it is. All right, so that is a limiting reactant problem. Oh my, come on video, there you go. All right, so again, kind of recapping here with limiting reactant, what stands out is you have quantities of two reactants, you're asked about a product, take first reactant to product, start over, take second reactant to product, look at your two answers, circle the smaller, right? That's your answer. So only 4.77 grams of H2S could be made because the reaction, what our calculations told us, HCl is going to run out first and limit how far the reaction can go, which means we're going to have a little bit of FES left over at the end. All right, so we're going to try one more of these. And then I think, oops, sorry. No, I'm sorry, we're going to do two more and then we'll take a break. Okay, so next one, I've got acetic acid, ethanoic acid, depending on which class you're in. So in organic chem, you start looking at this as ETH, two carbons. Oic acid means carboxylic acid, which is that OOH group at the end. So ethanoic acid in organic chem, acetic acid until then. And then you've got this I-pentanol, all means you've got an alcohol. So you got an OH group at the end. Penta, like we talked about, is the 5 carbons. And then you've got the pentyl acetate, which is different because acetates are different. But anyway, so this question says, calculate the percent yield if 19.2 grams of the I-pentyl acetate, so I'm going to write that down, I got 19.2 grams, was made from reacting 25.0 grams of the I-pentanol with the 25 grams of acetic acid. So this one is even more complicated because now I've got 3 numbers to deal with rather than just 2. So we keep making this a little bit harder. However, what I want to sort of stand out is that this question is asking us for a percent yield, right? That's really important to think about. If we want a percent yield, if that's really what we're looking for, the formula was we need the actual over the theoretical and then times 100. And what we talked about was when we do our calculations, that's our theoretical yield. So we know we're going to have to do calculations to get the theoretical yield. But the actual yield, because we're not in lab, has to be given. So a lot of times when I see percent yield questions, I see students kind of struggle with what am I starting with and where am I going? And I get it because you've got now 3 different things to think about. What I will always say, because this always works, is if you're looking for a percent yield, it will always be for a product, right? A lot of times when I see students going to tutoring, it drives me a little bonkers. They have students kind of back calculate and I'm like, no, you don't do percent yield of a reactant. That's not a yield, that's a consumption. That's a different calculation. Yes, technically it still can work, but it confuses students. Like, let's always just give them the same pathway. It'll always work. If I'm looking for percent yield, it's always going to be for a product. That I think that makes sense. So when I look at my reaction, right, the I-pentyl acetate, that's my product. Right, so that's what I want to know my percent yield of is the C7H14O2. And the reason why I point that out is because if I'm looking for the percent yield of that IPA, which in my brain means something different rather than I-pentyl acetate, but anyway, then the actual yield of that IPA should be given to me, right? Because in order for me to do a percent yield, I have to have the actual yield. So what I do is I say, okay, let me go find that. All right, actual yield, that has to be this 19.2 grams because that's what was given. All right, so I've got this 19.2 grams of I-pentyl acetate. That's how much was actually made. And I can get that from the question. That does tell me that. All right, that was how much IPA was actually made. Now my job is going to be to figure out, well, how much of that should have been made, right? So the reason for me kind of doing it this way is kind of saying, okay, if you're asked for a percent yield, it will always be for the product, right? It's always, if it's a percent yield, right? Yield means produce, right? So you're always going to be calculating a percent yield of a product. So what I'm going to do is look for the actual yield of that product. All right, and in this,
a quick
go
question,
ahead.
if I may.
Yeah.
What in ipentanol and apentyl acetate, what does the I mean? Is
Oh,
it some sort of just a fancy classification? Does it have any sort of bearing on the actual molecule?
so it's the structure. So when you have carbon, like a carbon chain, the question is it in a straight line? Is it a T? So the I is telling you whether or not it's just in a straight line or it's in a T. So it's more just the structure of the compound. And that can change the reactivity a little bit, but in organic, you'll learn more about that. So go ahead.
Keep going.
No, that's it. That's it.
Oh, okay. So at the end of the day, it doesn't really have much bearing on the answer for these sorts of questions.
No, not at all. Yeah,
Okay.
not at all. Yep, not until organic will that matter.
Well, structure is functionality, right?
Yeah, it definitely it can. Yes, and that comes with mechanisms and all other wonderful stuff from organic, depending on how the structure of the compound is. But usually the functional group is a better indication of what's going to happen, like what type of reaction will take place. Like, for example, back up here, the OL, that's an alcohol rather than an aldehyde or a ketone or something. But that's for about a year from now if you're headed in that direction.
All right, thank you for that extra information.
Yeah. So so the percent yield, right, will always be for a product. So we isolated that. It's going to be this ipentyl acetate. And if we're doing a percent yield, the actual yield has to be given. So we know that 19.2 grams is my actual yield. So what helps me understand is that, okay, that I'm just saving for later. So I've got my actual yield of the IPA. Then what I need is the theoretical yield, or TY, of the IPA. All right, so what I'm going to have to do here is I'm going to start with my acetic acid as my A1. The ipentanol is going to be my A2, and that IPA is going to be my B. It's going to be where I'm headed. So I've got a limiting reactant problem. First thing I'm going to have to think about is, okay, the 25 grams of acetic acid, how much of the IPA would that make? Start over. The 25 grams of ipentanol, how much of the IPA would that make? Just like we did in the last example. We circle the smaller, right? Because that tells us the limiting reactant. And those calculations are going to tell us the theoretical yield. And then what I can do at the end here is compare that to the actual yield that I got, which was given, sorry, the 19.2 grams. So these questions, I think, are the hardest of stoichiometry, because where we began with stoichiometry, we were just looking at one step, one calculation, right, from A to B. Then we complicated that with limiting reactant. And now we've got two calculations going from A1 to B and A2 to B, circle the smaller. Now what we've got is basically three calculations. We're going to take A1 to B, calculation 1, start over, A2 to B, calculation 2, circle the smaller, calculation 3 is doing the percent yield. So there's a lot of steps for this. So that's why I kind of tried to break this down. So first, isolate that the percent yield will be for the product, ipentyl acetate. The actual yield has to be given. The 19.2 was given. We pull that out. We save that for later. And I know now that the first thing I'm going to have to figure out is how much of that ipentyl acetate was I supposed to make. I know I only got 19.2, but how much was I supposed to get? So I start with my A1 and go to B. And I went ahead and grabbed the molar masses here, right? We've practiced that so we can save the time. All right, so starting with 25 grams. I've got 25 grams of the acetic acid. So CH3COOH, all right. And then the molar mass is 60.06 grams per mole. All right, I'm being lazy. I didn't put the substance down on the bottom. Then I need the mole to mole ratio. In this case, it is just 1 to 1. So 1 mole, I'm going to do AA for acetic acid, just to abbreviate. And it's going to 1 mole of the ipentyl acetate. All right. Oh, I should have used HAC because that would have matched what I had here. Okay, so we'll do that. HAC. Sorry, and this is HAC, and this will be HAC. Okay, and that'll match what I have up here in the question. All right, so we had our mass. Molar mass takes us to moles. Mole to mole ratio is just 1 to 1. All right, and then we need the molar mass of the IPA to get to grams, and that's 130.21 grams per mole of IPA. All right, so first calculation, how much IPA could I get? So 25 divided by 60.06, and then multiply by 130.21. And I could have made 54.2 grams of the IPA. But again, that calculation assumes that I have plenty of ipentanol to make this happen, and I don't. I only have 25 grams. So now I start over, and I have my A2 going to be. So I've got 25 grams of the ipentanol, so we abbreviated that as IPOH. On the bottom, molar mass, 88.17 grams per mole. All right, now mole ratio always in the middle. Again, it's 1 to 1. I know like on the test, if I have you write out the setups and you see that something is a 1 to 1 ratio, it's going to be tempting to leave it out, but don't leave it out because as your teacher, I want to make sure that you know that that goes there, even though mathematically it makes no difference. I want to know that you know that goes there. So even if it's a 1 to 1, or let's say it's a 2 to 2 or something, just please put it in, right? Leave it because you got to make sure you got that mole ratio step in there. All right. And then the last one here, 130.21 grams is 1 mole of IPA. All right. So let's see what the ipentanol would produce. So 25 grams divided by 88.17 and then times 130.21. So this one, 36.9 grams of IPA. All right, so like we talked about with the last example, the 25 grams of acetic acid could make about 54 grams of product. The 25 grams of ipentanol could only make about 37 grams of product. So we know that a limiting reactant limits how far the reaction can go. So the smaller of the two answers, right, the 36.9, not the 54.2, that right there is our max theoretical yield, right? In theory, if everything's perfect, that's what we should get. Max, because it tells me that the ipentanol was the limiting reactant. So my A2, the ipentanol, is the limiting reactant, which means the acetic acid would have been present in excess. Now I'm still not done after all of that. All right, so remember I said there's technically 3 calculations here. We did calculation 1, taking A1 to B. We did calculation 2, taking A2 to B, and now we need calculation 3, which is the percent yield. All right, so percent yield, actual over theoretical times 100, and it froze again. Okay. All right, so the actual yield, remember, we're not in lab, so we're going to get that from the question. The actual yield, it says 19.2 grams was made, right? So that's my actual yield. So 19.2 grams was made. I expected 36.9. And then percentage always means parts per 100. So 19.2 divided by 36.9 times 100. I know with percentages, a lot of times students want to round it to a whole number, but go ahead and keep your sig figs. So we've got 3 and 3. We're going to keep 3 for the decimal. So I get 52.0%. So that would be my percent yield here for this particular question. All right, and it froze again. All right, so those questions right there, that's a long question, right? There's a lot of parts to that. So just kind of reading through it again, this is just what I did. I always used my equation to kind of organize myself. So if I know, if I'm looking for a percent yield, that's calculation number 1 is going to, or in this case, it's the last one. But anyway, one of my calculations will be percent yield, which is actual over theoretical times 100. Since we are not in lab, actual yield has to be given. So I go and I look and I say, okay, well, actual yield, we're looking at a product that number of the product, that's my actual. So 19.2, that's my actual yield. Then the other two quantities I'm given are for two reactants. So I'm assuming this is a limiting reactant problem. I'm mixing the 25 grams of acetic acid and the 25 grams of ipentanol. They're going to do their thing. They're going to make that ipentyl acetate, and one of those reactants runs out first, and thus limits how far the reaction can go. And what we found, oh boy, is that once we made the 36.9 grams of IPA, the ipentanol would have been gone. And so that's why the reaction would stop at that point. And then my theoretical yield is based on that limiting reactant. So the smaller number, the 36.9, is my max theoretical yield. Then from there, actual over theoretical times 100 gets me to my percentage. So that's how I can finally get the percent yield for that question. All right, now one more question here. And it's on the next page. It's just one more like kind of simpler question. The reason why I like this question, I'm delaying just in case people are still writing, because I know that's a lot of information. A lot of the calculations we do in chapter 4, you'll see this, it's going to be a lot of them are going from mass to mass. And so students get really comfortable being like, oh, okay, I see this. There's always going to be 3 conversion steps. The first one is always the molar mass of A. The second one is always the mole ratio. The third one is always the molar mass of B. And in fact, I had a student, this is years ago when I worked down at the Gibbs campus. He had, and this is when I stopped allowing graphing calculators, but he had a graphing calculator, and he actually programmed his graphing calculator that the only thing he had to input was molar mass of A, mole ratio, and molar mass of B, and the calculator automatically spit it out for him. So he basically set up like a spreadsheet. And then when he got the test, he realized it's not always mass of A to mass of B, right? We can sometimes look at molecules. We can sometimes just look at moles. That's where we started with the very first example we did with the propane and the CO2. So you just have to be careful not to get too used to just always going mass of A to mass of B. That is probably our most common calculation here so far. If we're going to go into lab as chemists, that's right, because we don't have machines that measure how many molecules we have or how many moles we have, but grams, right, that we have. So I don't want everyone to forget that it doesn't always have to be that way. So that's the next example. And the last one we'll do before a quick break. So for this one, we've got 3 moles of nitrogen dioxide reacting with H2O, water, right? And we produce 2 moles of nitric acid and then nitrogen monoxide gas. And this one says if we've got 5 moles of NO2, okay, and 1 mole of H2O, and they combine and react completely, how many moles of the reactant in excess are present after the reaction has been completed? Okay, so first thing is I'm going to change this. I'm going to do this in 2 parts. All right, so I'm going to actually say first, I'm going to ask a slightly different question to go back to what I was talking to. First, I'm going to say, how many moles of NO would be produced? All right, and then the second question will be how many moles of the reactant in excess are present? All right, because that's another new topic from intro. We didn't probably do excess back in intro, at least I didn't. All right, so I've got 5 moles of NO2 in this question reacting with 1 mole of water, and we want to know how many moles of the NO are going to be produced. So what I was referring to earlier is this is not a mass of A to mass of B calculation. It's still limiting reactant because we have quantities of 2 reactants and looking for a product. So limiting reactant problem here. But because we have moles of everything, we don't need molar mass. Remember, we had talked, we only need molar mass if we have grams, and we don't have grams here. So whenever you're given moles, I want you to think, oh, wait, this is actually a step shorter, because normally my job is to always go to moles, but we already have moles. So we've actually saved a step. So if you are not given grams, then you don't need molar mass, right? If you're not asked for grams, then again, you don't need molar mass. So first thing here, if I take A1 to B, I've got 5 moles of NO2. If I set up my conversion step, for every 3 moles of NO2, because that's the coefficient from the balanced equation, I make 1 mole of NO on the product side. All right, so I'm not going to worry about sig figs here. I'm just going to go 2 sig figs. So I'm just going to go 1.7 moles of NO because otherwise it'll look kind of weird. All right, then if I go my A2 to B, for my second substance, I've got I got 1 mole of H2O. And in my balanced equation, for every 1 mole of H2O, I make 1 mole of NO. All right, so we're still following the same limiting reactant idea that we take A1, go to B, take A2, go to B, right? It's just what's different here and what makes it much simpler is that we're just going mole to mole. So we're just looking at mole ratios. So if I have 1 mole of water, I'm going to make 1 mole of NO. All right, so we know that that 1 mole of NO is our max yield, right? Because the water will run out first. So water is going to be the limiting reactant, which means the NO2 is going to be present in excess. And so that's something we've talked about on the previous limiting reactant problems. What is going to show up now in chapter 4 for Chem 1 is actually calculating how much of the excess reactant do you have left over. So we know that we're going to produce 1 mole of NO. So how much of that NO2 was actually used to make that? And we can see from the stoichiometry that if only 1 mole of NO was used, or sorry, was made, then only 3 moles of NO2 was used, right? Because if I make 1 mole of NO, I had to use 3 moles of NO2. So what we figured out from the limiting reactant portion of this was that the water was limiting. Since I only had 1 mole of water, I was only going to make 1 mole of nitrogen monoxide because it's a 1-to-1 relationship. So if I only make 1 mole of NO, that means I only used 3 moles of NO2. But the question said I had 5. So how many moles would have been excess? So we take 5 minus 3, and that means that there would be 2 moles of NO2 that would be excess left over. Never used it, right? And so the excess part of this, right, you can do that if you add to that the mass calculations. It's similar. You do that, you can kind of go through the same motions, right? If we added mass to this, that just means we have more calculations with the molar mass. But first, if this is still a limiting reactant problem, we know that because we still have 2 reactants, right? So we want to figure out how far this can go and then figure out which one's limiting. And then we can figure out how much leftover we have of the excess reactant. So that is actually where I'm going to take a little quick break for now. When we come back, I know it looks like we don't have too much more to do. We've got to talk about combustion reactions, reactions of alkali metals, and do a little bit more stoichiometry. So let's do, it's 12:23, so let's come back at 12:30. All right, so I've got 25 grams of NO2, and I'm reacting that with 25 grams of H2O. And the question says that those 2 reactants, they go to completion, but we're not concerned with how much product we're going to make like we typically are with the limiting reactant problem. Instead, we want to know how much of the excess reactant is not used up. So we understand that this is still a limiting reactant problem, right? Because we see that one of these is excess. That means the other one must be limiting. The problem is, though, is that when I have 25 and 25, even if I had one is 25 and one is 100, like you can't look at those numbers and figure out automatically which one's limiting. So this is a little bit harder. And I think the reason why it's harder is because it's a little bit more open-ended. When you don't have a clearly defined B, right? Like how much of HNO3 can you make, right? Then it's very clear. That's what you have to calculate. This is more open-ended. It doesn't really tell us how much product we're looking for. We just want to know, right? One of these is excess, how much is left over, right? So one of these is going to get used up entirely. And then the other one is going to have some left over. And that's the question, how much is left over? So that I think is harder, right? Because you're like, oh, I don't, what do I do? So this is the way I do it. I feel like this is the shortest pathway. There are multiple pathways. So what we talked about in the break was you could pick a product take your A1 to B, take your A2 to B, circle the smaller, you've identified your limiting reactant, and then you could back calculate how much of the excess reactant that you used up and subtract that from 25, and that would tell you how much is left over. And that is a perfectly good way of doing this. I think there might be a slightly shorter pathway. Now, first thing is, before we talk about the pathway, if I have mass, like we've talked about, I know the first thing I'm going to have to do is go to my periodic table and get the molar mass. So nitrogen is 14.01, 2 oxygens would be 32. So the molar mass of NO2 is 46.01 grams per mole. Hydrogen is 1.01 times 2, oxygen is 16, so 18.02 grams per mole for the molar mass of water. So I know I need that because I've got mass of each of those. So what I'm going to do here is, the first thing I'm going to do for this is I'm going to figure out which one is my limiting reactant. And this is going to be a little bit different than what we've done before. Normally, we figure out the limiting reactant by getting 2 answers and then circling the smaller, right? That's what we've looked at so far. Whoops, I went too many pages back. So we have our A1, we go to B, we take our A2, we go to B, we circle the smaller, and then we can go back and say, oh, well, that product meant that this reactant was our limiting, the other one was excess. All right, and that is one way to do it. But since we weren't asked about a particular product, we don't have to do it that way. So this is an alternative way of doing it. So what we're going to do is we are going to take our A1 and we're going to take our A2, and we are going to do 2 separate calculations. That's going to stay true. But because we don't have a B, we're going to make one up, right? We're going to have to anyway. Now, your choice, you could say, well, I'll just make my B nitric acid. Okay. Or I'll make my B NO. That's also fine. What I'm going to say here is my B is going to be reaction cycles. All right. And I'll show you what I mean by that. All right. And cycles, it's not really a unit. So I'm going to put this in quotation marks because it's not like grams, right? All right. So for my NO2, I've got 25.0 grams of NO2. Molar mass, 1 mole of NO2 from the periodic table is 46.01 grams. All right, now let me start over with my A2 here and then we can see why we have to have more steps. If I now start over with my water, I have 25.0 grams of H2O, molar mass of water, 18.02 grams. All right, if I stopped here, I would have moles of NO2 and moles of water. The problem is that the mole ratio of these two is not 1 to 1. So those numbers aren't comparable. What we have to capture is that I need 3 times as many moles of NO2 as I do moles of water. So that's this last step here. This is my B in quotes. For each reaction cycle, every time I do this reaction, I need 3 moles of NO2. For the water, each time I do 1 reaction cycle, I only need 1 mole of water because it only has a coefficient of 1. So if I look at my NO2, I've got 25 grams. If I divide that by 46.01, that means I have about a half a mole. And then if I divide that by 3, that means I only have enough NO2 to go through 0.181 reaction cycles. All right. And again, I put that in quotes because it's not really a unit, right? It's not like mass or moles. So now for the water, I had 25 grams of water. When I divide that by 18.02, I have a little more than a mole of water. And since I only need 1 mole per cycle, it means I could go through 1.39 cycles. All right. So what this math tells me is that I don't have very much NO2 compared to water in terms of how many reaction cycles I could do. The 25 grams of water could go through 1 1/3 cycle. The NO2 couldn't even get through a whole cycle. It can only do like 2/10, right? So what I'm looking at here then, when I look at those 2 numbers, is that the NO2 is definitely the limiting reactant. And that means that the water here is going to be in excess. So now what I know about my question is when it's asking me what mass of excess reactant, what I now know is that saying what mass of water is going to be unused. So now that I've identified that the NO2 is my limiting reactant, I'm going to take my 25.0 grams, always start with your limiting reactant, right? Because that limits how far the reaction can go. And my excess reactant is my B. That's really what this question is looking for. What mass of the excess reactant? That means what mass of water. So B is my excess reactant. So that's where I'm heading. So limiting reactant is always your A. It's where you start. Your excess reactant is where you're going to go. So this first part here was just to figure out which one was limiting. So the second part here, part 2, is to take the mass of the limiting reactant and figure out mass of the excess reactant that would have been used, right? So if I had 25.0 grams of NO2, 1 mole of NO2, same molar mass we saw earlier, 46.01 grams. Mole ratio, for every 3 moles of NO2, we need 1 mole of water. And there goes my video. And then for each mole of water, we would make 18.02 grams. So this is going to tell me that with that 25 grams of NO2, what mass of water would have been used up. So 25 divided by 46.01, divide that by 3, and then times 18.02. Now, some students are very comfortable with this and they can say, oh, well, this math right here is the same as that 0.181 answer. So I'm just going to take 0.181 and multiply it by 18.02. If you can see that, great. But a lot of times students want to kind of start over and go through the process all over again. All right, so this tells me I would only use up 3.26 grams of H2O. All right, and unfortunately, that's still not the answer we need. Part 3, step 3, is what mass was unused for the water. And the question told us we had 25 grams of water. We've only used 3.26 grams. So we're just going to subtract. And we remember with subtraction, we want to follow the decimal place rule. So we're going to round this to the tens place. So 21.7 grams of water would have been unused here. All right, so again, kind of complicated. I think know going in that if you see quantities of 2 reactants, it's going to be probably a multiple step calculation. But the mass of the excess reactant questions are typically three different calculations. You got to figure out which one is limiting first. And for that, you take the mass of each reactant, go to moles, use the molar coefficient to figure out how many reaction cycles you could do. The smaller one tells you your limiting reactant. The larger is your excess. So now when the question says what mass of excess reactant, you know what it's really saying is what is the mass of water. So we know the water is our B and the NO2 is our A. It's where we're going to start with. So we start with that 25 grams of NO2, figure out how much water we would need to react with that. So molar mass, mole ratio, molar mass, this is our mass of water that we would need to react with that 25 grams of NO2. I only needed 3.26 grams of water, but I had 25 according to the question. So 25 minus 3.26 means 21.7 grams would be left over. So quite a bit of water would be unused for that. All right, so that was a sort of a bonus problem in there, but I think it's probably good to do one of those calculations because you might see those in the homework. So finding the mass of excess reactant. And I had a Zoom session for my spring semester, and it has different problems on it, different example problems. So I'm going to leave that one up. So when you go into the chapter 4 folder, you'll see that Zoom session. It's either from January or February. And I'm going to leave that one up, and then I'll put the one from today as well. So that way you've got a couple of different sets of calculations you can look at as examples for chapter 4. But now what I'll do is I'll get back on track and go back and finish out the notes. So luckily the next section is just equation writing. So we won't be doing stoichiometry just for a little bit. We have to get back to it, but at least for a little bit, we can take a break. So where we left off, we were looking next at combustion reactions. So combustion, right? Burning, we can burn lots of things, but we're going to look at specifically hydrocarbons. And that makes sense. That's going to be a compound that contains hydrogen and carbon. They're not acids though. So the hydrogen, typically we don't write that in front. We start with the carbon to sort of signal it's not an acid, it's a hydrocarbon. And so we take that hydrocarbon, react it with oxygen. These are always exothermic. They produce a lot of energy in the form of heat. Right? We use octane for our gas in our car, propane in our gas grill, right? So these are good energy producers. And so the two products you always want to remember in a perfect world with perfect combustion are carbon dioxide and water, right? And we now, we understand every year right around this time when they start talking about hurricane season, they always remind us, hey, if your power goes out and you run a generator, you never run it inside your house, because that generator, which runs on fuel, does a combustion reaction. It's not a perfect combustion reaction. So instead of CO2, you get CO, carbon monoxide. And if you're in a closed space, right, carbon monoxide is obviously, it's not good, right? You got your iron center and your hemoglobin. Your iron center, unfortunately, it preferentially bonds with carbon monoxide over the O2. And so you suffocate because you just get real sleepy. Your oxygen gets depleted. You go to sleep and you don't have any oxygen. So that's what makes you pass away from carbon monoxide poisoning. So we are assuming that this is perfect world combustion. And so we are always going to predict carbon dioxide gas, which is much less toxic, and H2O. All right. So always remember those two. So those are the two. So combustion reactions, when I first learned these, I was like, oh, these are easy because I don't really have to predict products. I already know what they are. It's CO2 and H2O. The only thing I have to really worry about here is balancing. And as we talked about, oxygen is going to go last because it splits and goes into two places. So I'm going to just do carbon first. I've got 5 carbons on the reactant side in this pentane C5H12. And that's going to just go right over in front of the CO2 to balance the carbon. So we're going to just take that subscript and make it the coefficient for CO2. And that's done, nice and easy. With the hydrogen, we've got 12 hydrogens on the reactant side. And when I come over to the product side and I balance the hydrogen, because hydrogen is coming out as water, which is H2O, I need 2 times some number to get to 12 because, right, I need 12 total on the product side to balance the 12 on the reactant side. So the coefficient in front here is going to be a 6 for the water. So 2 times 6, there's my 12. And now I have balanced the hydrogen. And the last thing I'm going to look at is balancing the O2. So when I look at my oxygen, and I'm just going to switch my pen colors here really quick so we can track it. The 5 times 2 means I've got 10 oxygens. And then 6 times 1 means 6 more oxygens. So I have a total of 16 oxygens on the product side. And so when I come over here to the O2, again, 2 times what number is going to get me to 16. And I need a total of 16 because that's what I have on the product side. So 2 times 8 is what gets me to 16. So I put an 8 in front of the O2. All right. So if we try one more here, I've got C12H22. And again, the 2 products, CO2, gas phase, water also in the gas phase because it's burning. We're past the boiling point of water. It's coming out as steam rather than as liquid. All right. And then quick balance with the carbon. That's the easy one to do first. I've got 10 in the hydrocarbon. So just carrying that over in front of the CO2, we're going to put a 10 in front. And then for the hydrogen, I've got 22 on the reactant side. So 2 times what gets me to 22 total? I need an 11 in front of the H2O. All right. And anytime you end up with an odd number in front of water, you're going to end up with an odd number of oxygens. And that's okay. I'll show you how we can fix it. So if I look at my oxygen, 10 times 2, I've got 20 oxygens. And then another 11 in the water. So I have a total of 31 oxygens on the product side. And if I'm going over to my reactant side and balancing that, 2 times what gets me to 31. So I remember when I first started teaching and I was looking at textbooks, they never used decimals. They always used fractions. So they would put 31 over 2, right? Because 31 divided by 2 times 2 gets you to 31. And then I saw where they did use decimals, and they would put in 15.5. It doesn't really matter, right? It's to me, mathematically, those are the same. But in the answer keys with a lot of textbooks, they won't use fractions or decimals. So like if you were checking your answer in the back of the book, and it wouldn't show up as this, it would show up slightly differently. So if you get an odd number of waters, then just know you have to start over by multiplying by 2. Everything's just going to have to end up multiplying by 2. All right. And there's my frozen screen again. Okay. So I know I don't really have a ton of room here, so I'm going to just show it right down here. So instead of 1 C10H22, you would have 2 C10H22. We'll come back and do the oxygen here in a minute. Then on the product side, instead of just carrying over that 10, if I have the 2 now, I've got really a total of 20 carbons. So I'm going to put a 20 in front of CO2. And that makes sense because I'm multiplying it by 2. So 10 times 2 is 20. And then for the water, instead of 11, it would be 22. But if I double check that, 2 times 22 is 44. 2 times 22 is 44. Now, when I balance my oxygens, I've got 40 in the carbon dioxide, plus another 22 in the water. So that'd be 62. Then in front of the O2, a 31 times 2 gets me to 62. So I've got the same equation. Everything's been multiplied by 2. So 1 times 2 became 2. 31 divided by 2 times 2 becomes 31. 10 times 2 becomes 20, and 11 times 2 becomes 22. So to me, these are equivalent. But a lot of times, like I mentioned in textbooks, they'll want whole numbers for the coefficients. And so they'll just make everything whole numbers by starting over with the hydrocarbon having a 2 in front. But combustion reactions always produce CO2 and H2O. Always just remember that. That makes these really easy. And basically, when you go to balance, just make sure you do the oxygen at the end, and then that's it. That's all there is to that one. We'll do more complicated reactions in the next chapter after our first test. We have another set of reactions to do here. And
I have a question.
Yeah, go ahead.
So you do the multiplication by 2 after you get your formula, or could you do it before?
It's up to you. If you kind of can look ahead on this and you say, oh, 22 divided by 2, I'm going to have an odd number here in front of water. If you can see that, then you can just go ahead and start by multiplying it by 2. But a lot of times what I'll find is students will kind of do this part. Oops. They'll do the 10 in front of the CO2 and the 11. And then once they do that, they're like, oh, okay, I'm going to have to multiply by 2. And they'll go and they'll put a 2 here, change this to a 20. Okay. And then change the 11 to a 22. Oh boy. And then once they have that, the 2, the 20, the 22, then they'll start and balance the oxygen at the end.
Okay, thank you.
Welcome. All right, then the other type of equations that we have in this chapter are alkali metals. So if we remember from our first chapter of work, our alkali metals, right, are those group 1 metals. So lithium, sodium, potassium, rubidium, cesium, francium, right? So those are our alkali metals. And when we react them with halogens or oxygen, it's going to be a combination reaction. The big thing to remember here is that these are going to be diatomics. So we talked about this in chapter 2, that there are 7 diatomic elements. I think it was chapter 2. Now I'm doubting myself that maybe it was in, but there are 7. We talked about Hofbrinkel, and those 7 elements, just those 7 elements, and just those 7, that they're never really by themselves. They occur diatomically because that's how they're stable. So when I look at reacting with a halogen, like chlorine, bromine, iodine, or fluorine, it's going to be Cl2. It's going to be a diatomic, right? So Cl2 or Br2. If it's oxygen, same thing, oxygen would be O2. So what you have here is you start with the element, the alkali metal, no charge, the halogen or the oxygen as a diatomic, also with no charge. And this is a redox reaction, which means the metal is going to lose electrons and become a cation. and the nonmetal is going to gain electrons to become an anion. So when we put the two together, we can see that. We can see metal and nonmetal, so this should be an ionic compound. So now we have to think about charges. Sodium being a group 1 metal, all the alkali metals, right? They carry a +1 charge. The halogens we know are going to be a -1 charge. So +1, -1, just a 1-to-1 ratio. But now to balance, because the chlorine was diatomic, I have to have 2 sodium chlorides, which means I have to have 2 sodiums. If I change this and look at oxygen, if I had sodium, again, there's no charge here, reacting with oxygen, again, no charge. On the product side, when I put them together, sodium, again, alkali metal +1, oxygen becomes a -2 charge. We remember that from position on the table. Halogens, we know -1, oxygen family -2. So when I look at sodium oxide, it's not going to be NaO, it's got to be Na2O to balance out the charges. +2, -2 cancels out. Now to balance, there's 2 oxygens on the reactant side because again, it's diatomic. And so I need 2 on the product side. So I put a 2 in front of Na2O. Now 2 times 2 gives me 4 sodiums. So I put a 4 in front of Na. So the alkali metals, when they start this type of combination reaction, they don't have a charge. They are in their elemental form. This is a highly exothermic reaction, by the way. Sodium, all alkali metals are highly unstable. They love to give up their 1 valence electron to become an ion. And by love, I mean they give a lot of energy when they do it. And then the halogen, the diatomic, also starts out with no charge. All of its electrons are just how it comes on the periodic table, but it is diatomic. Same with oxygen. And then on the product side, we make metal and nonmetal, so we make an ionic compound. So now we think about charges. So the combination always results in an ionic compound. So we balance out the charges appropriately, like we learned with nomenclature, and then we can balance the equation. And I've got more examples on the last page for us to look at. The other type of reaction we can have is a single displacement reaction, which is what happens when the alkali metals react with water. So alkali metals, alkali means base. And the reason why they're called that is because when they react with water, they turn the water into base, which is hydroxide. So when we do acid-base reactions, we'll see that hydroxide is our base. In fact, that's one of the definitions, is that if it's a base, it turns water into hydroxide. So the alkali metal, again, starts out no ion. It's in its neutral form. There's no charge. And it reacts with the water and always produces hydrogen gas, right? And the metal hydroxide. And this is, as I mentioned, extremely exothermic. A lot of heat is generated, typically so much so that the hydrogen, which is a flammable gas, will catch fire. So those are kind of fun reactions to Google if you're interested, like reaction of sodium with water, reaction with potassium with water, something like that. But they're all going to kind of look the same. So the only thing that would be changing for what we're responsible for right now is just the alkali metal. The water is going to stay the same. So if I change this, let's say to potassium, again, it starts out no charge, and we react it with water. And on the product side, we produce the potassium hydroxide, right? That's always a definite. The water is always turned into the base. So it's always this metal hydroxide, like we just saw with the sodium. And the other product that's a definite is the hydrogen gas. That's always produced as well. So then the only thing we have to do is balance. And again, hydrogen we do last. So let's look at oxygen looks okay so far, 1 and 1. Potassium looks okay so far, 1 and 1. Now, when I look at the hydrogen, I've got 2 on the reactant side, but 3 on the product side, which makes me think, well, that's not going to work, right? So if I put a 2 in front of water, now I've got 4 hydrogens and 2 oxygens. 2 of the hydrogens are in the H2. If I put a 2 in front of KOH, there's the 2 oxygens and the other 2 hydrogens. 2 plus 2 is a total of 4. And then the 2 potassiums, just to balance, I need a 2 in front of the K. All right, so that is the reaction of an alkali metal with water. And the only thing that would change there is the alkali metal, but otherwise everything else stays the same.
Excuse me.
Yep.
I'm just a little confused because of this. I thought it was just single displacement, so it'd just be KOH2, not KOH H2.
Okay, so the single doesn't mean that there's a single product. Oops, sorry. And that, yeah, you're right. Normally in intro, when we present single displacement, we present double displacement at the same time. And then I think it makes more sense why they're called that. In a single displacement reaction, you have a single element and it's displacing the cation. So the sodium and the hydrogen are switching places. The hydrogen comes out by itself, and the sodium goes in the compound. So really, if you think about water, you know, it's really HOH, right? We don't ever write water that way, but that really is the structural compound. So the sodium and the hydrogen are switching places, and the sodium goes with hydroxide. So that's why it's called single displacement, because just a single thing is switching places. Is that what you mean?
I understand now. That's why Miss Mitchell always said to keep it HOH, not H2O, because it
Yeah.
creates confusion.
Yes, I think that's good advice. And for some, but we just never write H2O as HOH, even though that is the structural formula. We always write it as H2H, and that also is helpful in acid-base reactions too, to write it as HOH. But yes, that's what's happening. The single element right there is switching places. Okay, so if that's good, then we're going to go to the last page, and we've got some kind of review questions. We're going to do a little bit of equation writing, and we're going to do some more stoichiometry just to kind of wrap up the chapter. So this one says we've got solid potassium metal. All right, so potassium is K, metal means we've got a solid, combines with oxygen gas, and instead of just O, right, oxygen is part of Hofbrinkel. So Hofbrinkel, right, those are our 7 diatomic elements, so we got to put it as O2. And what forms is potassium oxide. So if I'm putting potassium and oxygen together, metal and nonmetal, this is going to be an ionic compound. Potassium is +1, oxygen is -2. So the formula there has to be K2O. So that's the first part, just writing the equation. We've got potassium, right? Not part of Hofbrinkel, so it's not a diatomic, it's just singular. Oxygen, part of Hofbrinkel, so diatomic. And then potassium oxide, that's what we did in nomenclature with credit quiz 2. Metal, non-metal, think about our charges, balance them out. Now for balancing the equation, since I've got 2 oxygens on the reactant side, 1 on the product side, I'm going to multiply the K2O by 2. And then when I put that 2 in front of the potassium oxide, 2 times 2 means I have a total of 4 potassiums. So 4 in front of the K on the reactant side. So I've got my balanced equation. So the big thing here, I think that students just forget is that when it's talking about oxygen gas, right, that's elemental oxygen, just make sure you make it a diatomic. If we're talking about oxide, then it's not oxygen. That they're 2 different things. Oxide is the oxygen that's in an ionic compound. And so then what we think about are the charges, and it's singular. It's only when oxygen is not as an ion that it's not by itself. It has a subscript of 2. And we saw that with the combustion reactions as well, right? It was the hydrocarbon reacting with O2 gas. So this question says, what would be the percent yield if 82.5, that's obviously a typo, grams of potassium oxide, all right, so 82.5 grams of potassium oxide was formed from reacting 75 grams of potassium and 75 grams of oxygen. All right, and again, what I focus on here is that the question is asking me for a percent yield. So like we talked about previously, I know that means I need an actual and a theoretical yield of a product. And that will be, the product will be for the K2O, because that's my product. So the next thing we talked about was, okay, well, if you're doing percent yield, actual yield has to be given. So that 82.5 grams, that's my actual yield, right? I actually got 82.5 grams of potassium oxide. So the first thing I need to do is figure out, well, how much potassium oxide was I supposed to get? All right. So step 1 here is to determine the theoretical yield of K2O, the product, right? Because if I have my actual, I need the theoretical. Now I have 2 reactants. I've got the potassium and the oxygen. So I'm going to have 2 calculations here. So starting with my A1, I have 75 grams of potassium. Oh, and my pen is dying. So, and my screen is is locking up. Okay, so this has been a challenge for me today. I'm having technical troubles today. All right, so in this first calculation, I've got the 75 grams of K. And I know, like we talked about, if you have a mass, you need a molar mass to get you to moles. So if I go to my periodic table, 1 mole of potassium is 39.10 grams. Just grabbing that mass number. Next thing I do, my mole to mole ratio. For every 4 moles of potassium, I produce 2 moles of K2O. And then if I want grams, which I know I need because my actual yield is in grams, I need the molar mass of the K2O. So 39.1 taken twice, added to the 16 for the oxygen is 94.20. All right, so if I first do this calculation, so 75 divided by 39.1 times 2 divided by 4, and then times 94.02, I get 90.2 grams of K2O. All right, but we know that may or may not be our answer. So now we start over with the A2. We have 75 grams of oxygen. 1 mole of oxygen is 32 grams because each oxygen is 16 from the periodic table. Mole ratio in this case, for every 1 mole of O2, we make 2 moles of K2O. And molar mass is the same because we're going to the same place. So 94.20 grams for 1 mole of K2O. All right, so for this calculation, 75 divided by 32 times 2 times 94.20. And I get, I'm going to type it in one more time. 75 divided by 32 times 2 times 94.2. Okay, yeah. I get 442 grams of K2O. All right, so that is definitely a lot more than the other one. Come on, video. There we go. So when I look at the two calculations, what we understand is that the potassium is our limiting reactant. See, I just typed that in again. Hold on. 75 divided by 39.1. 2 times, I think I put O2 in my brain instead of 0.2. Yeah, so I got 90.3 when I did this again. I think when I kind of caught myself, I think as I was like thinking about this, I think when I typed it in, I typed 94.02, but 94.20. So that was 90.3 for the answer. Sorry. Okay, so we can see from this, we circle the smaller, right? This is going to be our theoretical yield, the 90.3 grams of potassium oxide, because it tells us that the potassium here is going to be the limiting reactant. And the final part of this is to figure out the percent yield. And so what I know here is I had an actual of 82.5 and a theoretical of 90.3. So I'm going to put that over in the margin over here just because I'm like running out of space. So percent yield, 94.20, sorry, what I had potassium is 39.1 from the periodic table. And if I take that twice, that's really 78.2. And then if I add 16 for that, for the oxygen, that's where I get the 94.20 from. Okay, all right, so my percent yield. So this one, oh, so the 442, I took 75, let me type it in, divide by 32, and then times 2 and times 94.2. Yeah, so I got 442. So I took, oh, okay, no worries. Okay, so I've got my 2 mass of products. And like we talked about with limiting reactant, the smaller is our theoretical yield. So only 90.3 grams of potassium oxide can be made. Potassium is going to be my limiting reactant. It's going to run out first. I have my theoretical yield of 90.3. Based on the question, the actual yield was 82.5. So I'm going to take the 82.5 grams of potassium oxide actual divided by the 90.3 grams theoretical times 100. I'm going to keep my sig figs at 3. And what I get here is a 91.4% yield. All right, so after all that, we were able to figure out the percent yield, 91.4%. So for this question, kind of just tying in some things, we did our alkali metal with oxygen that we just looked at on the previous page. Then we added to that this limiting reactant question, and then on top of that, the percent yield calculation there. So a lot going on with that question. Number 2 is also going to have a little bit going on with it as well. So question number 2 says, what mass of carbon dioxide would be generated from the combustion of 15 gallons of octane, C8H18, which has a density of 0.703 grams per milliliter? All right, so first thing is, I recognize that I'm looking for carbon dioxide. Oh, that's the pen that died. And I'm also given octane. So the first thing that my brain thinks of is, oh, those are 2 different substances. So I need an equation, right? I'm going to have to come up with the balanced equation. And I'm doing a combustion reaction that also sort of sticks out. So I've got this C8H18. What I remember about combustion is oxygen is the fuel for fire. And I'm going to always produce, right, in a perfect world, carbon dioxide and H2O. Now, balancing this, the 8 carbons means an 8 in front of CO2. Now, really, that's the only mole ratio I need here. So I could stop if I wanted, because I just need to compare those 2 things. But since we are learning combustion reactions, let's go ahead and finish it out. I've got 18 hydrogens, so 9 in front of the water to get me 18. This is that step I talked about earlier, that if you see an odd number in front of water, you know you're going to have an odd number of oxygens. So if you want to do a whole number, then you would start over here and you would have a 2 in front of the octane. The 8 is going to become a 16, and the 9 is going to multiply by 2 to become an 18. All right, so if you prefer to have the whole numbers, right, we'll do it that way. So just multiplied everything by 2. The last thing I got to do is figure out the oxygen. So 16 times 2 means I've got 32 oxygens here. 18 times 1, right, is 18. So I have a total of 50 oxygens on the product side. So times 2 in front, I need a 25 in front of the O2. So now I've got my balanced equation. Now the question is, what mass of carbon dioxide, so how many grams, would be generated from the combustion of 15 gallons of the octane? And I've got a couple of things. I've got the conversion of gallons to liters, and I've got a density. So let's just kind of get started and see what's going to happen here. Now, the good news is, before we start, oxygen was not mentioned. So we assume that this is excess, which is nice. That means that this is not a limiting reactant problem. And I also don't see any mention of a percent yield. So we at least don't have that to worry about. So I know that the octane is where I'm starting. The CO2 is where I'm going. Let's just kind of start thinking how we're going to piece this together. So I have 15 gallons of the octane. What I remember is that a gallon is 3.785 liters. That was one of the conversions in chapter 1 that I did want you to remember. Now, where do I go from here? We've gotten very used to doing mass to moles. What happens if we have a pure liquid like octane? What do we do for that? Well, I see that there's this density that's given to me, and I wouldn't give you something unless you need it. So I'm going to go in this direction. I'm going to go to milliliters. I have a unit of liters, so I'm going to get it into milliliters. So 1 milliliter is 10 to the negative 3 liters. Again, if you prefer 1,000 milliliters is 1 liter, that also works. Then the density, 0.703 grams per 1 milliliter. And I knew milliliters had to go on the bottom to cancel out. So these first conversions basically tell me my mass of octane. And so that's helpful because then I know I can use molar mass to get to moles. All right, so I'd have to go to my periodic table. That's supposed to be a 1. All right, add 8 carbons at 12.01 apiece. And, whoops, sorry, 12.01 times 8. And then the 18 hydrogens would be 18.18. So I have 114.26 grams per mole. That's my molar mass. All right, then I need, now that I have moles of A, I need to do my mole to mole ratio. So for every 2 moles of C8H18, I make 16 moles of CO2. All right, and then the last thing there, I know I'm running out of room, is to get to grams. So carbon dioxide, 2 oxygens is 32. A carbon is 12.01. So that's 44.01 grams per mole for the molar mass. All right, and this is for the CO2. All right, so that says 44.01 grams per 1 mole of CO2. So what I did here is I took, just for the unit conversion, I took gallons to liters first, then to milliliters. So that was just chapter 1 material unit conversions. Then I took milliliters to grams using density. That's what the density was given to me for. Then once I had mass, I could go to moles. All right. And so that's the molar mass from the periodic table. Then from there, I could switch and go to moles of B. That's the ratio that we look at from our balanced equation. And then after that, we can go to mass of B using our molar mass from the periodic table. So the first half of this is like chapter 1, and the second half of this is chapter 4. All right, chapter 3 and 4. So that was the flow chart. Now the calculator, 15 gallons times 3.785 means I had about 57 liters. And then if I do the conversion to milliliters, I've got about 57,000 milliliters times 0.703 means I have about 40,000 grams. Divided by 114.26 means I have about 350 moles of octane. Then if I include that mole ratio, it means I have about 2,800 moles of CO2. And then if I multiply by the molar mass of CO2, it means I have a lot of grams of CO2. All right, so I'm going to just type it in again really quick. All right, so 15 times 3.785 divide by 1 times 10 to the negative third times 0.703, and then divide that by 114.26, then times 16 divided by 2, and then multiply by the molar mass of carbon dioxide, which is 44.01. Calculator gives me 122,987 grams of CO2. All right, and if I'm thinking about 2 significant figures, 1, 2, and then replacing 1, 2, 3, 4 digits with zeros, or 1.2, and then scientific notation, right? We're moving it 1, 2, 3, 4, 5 to the left, so positive 5 on the exponent. Okay, so that is a stoichiometry question as well. It's just instead of starting with a mass like we were getting used to for a pure liquid, we would maybe use the volume instead, right? Instead of how much mass we have, what volume do we have? And then just to kind of throw in a little bit of a curve, I gave gallons instead of milliliters. But the thing to keep in mind here is that if you have a pure liquid and you do measure the volume that you have, density is your friend to get you to mass. And then once you use density to get to mass, then you can do the traditional molar mass. We don't have a direct path from volume of a pure liquid to moles. We have volume of a solution to moles. That's molarity, if you remember that, but we don't have that for a pure liquid. Pure liquids don't have a molarity. So that's why we have to use density instead to get to grams first. All right, so I think that's it for chapter 4. So Tuesday when we meet back at 11:15, we'll be going through the test 1 review. And then just as a little reminder, your chapter 2 credit quiz, right? That's due tonight at 11:59 p.m. But Tuesday, when I see you back, we'll be doing our test 1 review. Test 1 opens up Wednesday next week and closes Friday. So for now, just today, get through chapter 2, then start looking at chapters 3 and 4. But that'll be where I stop for today.
Excuse me.
Yeah.
Can you do me a